Hello, everyone, and welcome to this webinar titled Radar Cross-Section Analysis Using Feko. This event is a result of a collaboration between IEEE Ottawa, AP MTT chapter, and Altair, as well as other various IEEE chapters and affinity groups. Today's presenter is Gopinath Gampala, who is Manager, Global Technical Team at Altair. Gopi, thank you very much for being with us today. Please take it away.
Thank you, Ahmed. Before I start, just want to make sure you're recording this one, right?
Yes, the meeting is being recorded.
Okay, thank you. So, hello, everyone. So unfortunately, CJ could not join today, but I have my colleague, Evan, joined. So he will be monitoring the chat. So if you have any questions during the webinar, please post your questions in the chat. Evan will try to answer them as they come in, but if there are any more questions left, yeah, we can definitely take some questions at the end of the webinar as well. So maybe like before I get into the outline and everything, just want to also let you know that this is part of a series, kind of series that we are doing. I think this may be the fourth or fifth one. The previous ones covered several different topics like antenna design, EMCMI, wireless coverage. So today it's on radar cross-section analysis. But before going into the topic, I just want to let you know that instead of using the big word radar cross-section, we'll just use the acronym RCS for the entire duration of the webinar. So it's simple and easy. Yeah. Now, coming to the topic of RCS, most of us may not realize it, but we benefit from RCS applications on a daily basis. Okay? Like when we are like checking the weather, or when you are flying, or when you are driving a car, in so many different ways, RCS is affecting our daily lives. Okay, so today let's try to learn some basics of RCS and how Feko can be used to compute RCS of any given target. So this is the outline of today's webinar, the different topics that we try to cover today. We'll first look into some basic introduction to RCS, followed by different options in Feko for RCS analysis and the complete workflow in Feko to set up a model and compute RCS. Okay? And wherever it is applicable, I'll try to show the Feko interface with an example model, like a live demo, so that it's not just looking at the slides, but you get an opportunity to look into some real models. Okay. Then we will look into different solvers available in Feko for RCS calculations. Because when you're trying to calculate RCS of any target, depending on the frequency, the target size may be certain wavelengths. If the target is electrically small, some solvers may be efficient. As the electrical size becomes large, then the computational resource requirement may be more demanding. So we try to limit that by using some other solvers which may be more efficient for electrical large structures. So we will look into all those things. And there are also some utilities in Feko for RCS post-processing, like ISR imaging. So we have a fully developed macro available for ISR imaging. We will look into that. And Feko also supports all different types of materials. They can be metallic or dielectric or even composite. Okay, so we will also look into like how you can define composites in Feko. And last but not least, we'll look into some of the student resources available. So you can all benefit from those resources. Okay. So what is RCS? It is nothing but a unit of measure of how detectable an object is with the radar. Okay. So RCS of any target is measured with a radar, which uses radio waves or electromagnetic waves. Okay. The radar sends out pulses of electromagnetic waves and then listens the echoes bounced back from the target. The amount of power that is reflected back from the target to the radar depends on the target's RCS. Okay. So RCS is nothing but the fictitious area that describes the intensity of the electromagnetic wave reflected back to the radar. Okay. So what are the different applications of RCS? Okay. As I mentioned in the beginning, it finds applications in a wide range of disciplines, including air traffic control. As I said, when we are flying, the air traffic control monitors all the different flights in the air. Those flights are detected using a radar. Okay. So without the radar, it will be hard for us to fly. And there are applications in military and defense. So why for civilian aircrafts, where we want the aircraft to be detectable so that it can be tracked along the flight journey. For defense applications, they try to design these fighter jets with minimal RCS so that they are invisible to the radar. They're not being easily detected by the radar for stealth applications. Okay. And we also find radars in automotive applications, like there is the ADAS radar, which is at the front bumper of the car for adaptive cruise control. Okay. So in those automotive applications also, the idea is for the target to be detectable as much as possible so that one car can see the car in front and avoid collision. Okay. And RCS also finds applications in radar meteorology, like if you want to check the weather. So I said, like for civilian applications, we want the target to be detectable, but for defense or military applications, we want the target to be invisible to the radar, right? So this is an example, just comparing two different planes. One is a civilian aircraft, the other one is like a fighter jet. If you look at the RCS of a passenger aircraft, you can see the blue curve, which has a high RCS, so it can be easily detected. Whereas the fighter jet on the right, you can see its RCS is much lower compared to a passenger plane. Okay. Now, let's try to define RCS in a form which we can understand and use that to calculate or compute the RCS of any target. Okay. So to define RCS like in the form of an equation, we will first try to understand few terms. The first one is the geometric cross-section, which refers to the area the target presents to the radar, which is also called the projected area. Okay. And the geometric cross-section varies depending on the angle or the aspect the target presents to the radar. Okay. So it determines how much power transmitted by the radar is intercepted by the target. Okay. So this is a simple expression that relates the geometric cross-section, the power intercepted by the radar, to the power incident or the power emitted from the radar. Okay. The next term is reflectivity, which refers to the fraction of incident power that is reflected by the target, regardless of the direction. Okay. So if you take for example, like an isotropic emitter, it emits power equally in all directions, right? Whereas if it is not isotropic, then the power is not equal in all directions. Similarly, when the radar emits some power and it's instant on the target not necessarily reflects or scatters equally in all directions. Okay? The power re-radiated or scattered after reflecting off the target is equal to the intercepted power less whatever portion absorbed by the target. Okay? So with this, we can define reflectivity as the ratio of power scattered by the target to the power intercepted by the target. The next term is directivity. So now it is nothing but the ratio of power that is back scattered in the direction of the radar to the power that would have been scattered in the same direction if the scattering were uniform in all directions. Okay? So in practical applications, that's not the case. That's why the directivity is nothing but the power reflected by the actual target to the power reflected by some isotropic one, which theoretically reflects uniformly in all directions. Okay. Now that we have these three terms, geometry cross-section, reflectivity, and directivity, now we can define the radar cross-section as a function of all these three different terms. So if you see RCC is geometric cross-section times reflectivity times directivity, which you can put in terms of 4 pi P backscattered over P intercepted. Okay. Now, whenever you try to compute RCS, let's say if you're trying to compute RCS in Feko, you typically use plane wave as an excitation with an instant field of E naught. So if that is your instant field, and we are looking at the scattered field, you calculate the fields everywhere in different directions in terms of E theta and E phi. Now, to put RCS, the total RCS would be if a magnitude square of E theta plus a magnitude square of E phi over the square of instant field. Okay? So this is the simple expression that one can use to calculate the RCS or to compute the RCS. Okay. And this is what we typically do it in the background in Feko. So as a user, when you're trying to use the software, you don't do any calculations, but this is what happens in the background. So before we look into some examples of RCS using Feko, I just have one slide here to introduce what is Feko. It's a 3D high-frequency electromagnetic simulation software which offers multiple frequency as well as one time domain technique with true hybridization, meaning in the same problem, it's possible to use multiple solvers to solve it efficiently. Okay. And because there are so many different solvers within one tool, it can be used for many different applications. Okay. So if you see here, the different applications, we already covered all these different applications like antenna design, antenna placement, EMC, EMI in the previous webinars. And the recordings of all those webinars are on the IEEE Ottawa YouTube channel. So you can go there and watch those previous recordings. But today's topic is RCS, which falls under the scattering applications. Okay. So that is just one slide introduction to Feko. Now we will jump into the main topic, which is RCS calculations in Feko. Now to calculate RCS, typically you calculate in different polarizations, and any polarization that you want to use to calculate your RCS, it is supported in Feko. And the most commons are typically the horizontal and vertical polarizations. So when you look at some RCS plots, you might see like HH or VV polarization, which basically means the first H will be horizontal polarization of the transmitter, the second H will be the receiver polarization. And in VV, so same thing, the first V is the transmitter polarization and second V is the receiver polarization. And in Feko, you can, whenever you calculate the monostatic RCS, the polarization being treated as same for the transmitter and the receiver. And as I said, you typically use a plane wave as an excitation to calculate RCS in Feko, right? So when you're trying to define a plane wave, you see these kind of options where you have the option to control the instant field direction as well as the polarization. Okay. And the instant field can be either in a single direction or it can be over multiple directions. Okay. But there are two different RCS quantities you can calculate. One is the bistatic RCS, the other one is the monostatic RCS. Okay. When you are trying to calculate the bistatic RCS, then the transmitter and receiver are not in the same direction, same place. Whereas for monostatic RCS, both the transmitter and receiver are in the same place. Okay. Now to compute bistatic RCS using Feko, once you have your instant field specified, then you can request for the far fields or the RCS in any direction of your choice. So the receiver position is defined using the far field request. So it need not be in the same direction as the instant field, making it a bistatic RCS. But if you are to calculate the monostatic RCS, then you go with the option calculate fields in plane wave instant direction. So that makes the transmitter and the receiver to be in the same direction, making it a monostatic RCS. Okay. Those are the different options in Feko for computing RCS, right? So let's go through it through a live example. So we'll look into an example of computing RCS of a sphere. So let me open Feko. So when you install Feko, you have a Feko launcher where you have access to all the different software. If I start a new project, typically you always start with CAD Feko, which is the pre-processing interface of Feko. And here you have the option either to import the geometry of the target for which you want to compute the RCS, or you can create the target shape using the geometry primitives in Feko. And there is also a component library that comes with the installation. It's a library of many different pre-designed antennas, but there are also some models for like a helicopter or like a CubeSat or like a car back. So different targets, if you want to use some of these as your targets to calculate RCS, you can. But there are some benchmark shapes. Let's say people who develop some codes to compute RCS, if they want to validate their code, they can use these different targets to compare the RCS computed using their code with what is expected out of all these different standard targets like almond, cone sphere, or cone sphere with a gap, or ogive. Okay. And these standard targets are also part of the component library. Now, to compute RCS, first you need a target, right? Let's say our target is sphere, so we can model a sphere easily using the geometric primitives in Feko. So once you have the target, the next step is you need to specify the frequency where you want to compute the RCS, whether it is at a single frequency over multiple instant angles or over a frequency range. So you can go and you can specify either a single frequency or a frequency sweep. Okay. For example, let's say I compute RCS at 300 megahertz. So you can see as soon as I specify frequency, depending on the frequency as well as the material properties of the geometry, Feko will automatically mesh the model. And then for computing RCS, we use plane wave as an excitation. So you can click on plane wave. And this is where you have an option to specify the instant direction, whether it is a single instant wave or you want to loop over multiple directions. Let's say you want to calculate RCS in the azimuth plane. Then along the z-axis, that's theta is equal to 0. So to change the incident angle to the azimuth plane, you can change the theta to 90. And let's say you want to sweep in the azimuth plane, then you can sweep your phi, let's say for example 0 to 90 degrees. Because you are sweeping phi, you can also specify an increment. There is no limitation on how fine you can go. Instead of phi, I can even go like 0.1 degrees or 0.01 degrees. There is no limitation from the software side how fine of an increment you can use for your incident angle. Okay. And for polarization, if you look at these arrows, the blue arrow indicates the incident field direction, whereas the green arrow indicates the E field vector. Okay. Now, because the E field vector is vertical, so this is vertical polarization. Now, if you want to calculate RCS in horizontal polarization, you can rotate your E field vector by changing the polarization angle. So if I change it to 90, you can see the green arrow rotated. Now it is parallel to the horizon, making it horizontal polarization. So this way, you can always control the polarization. Okay. If I click on create, that will add the excitation. So once you have the incident field, then you need to request for RCS, which is a far field quantity. So you can click on far fields. For bistatic RCS, then you will specify the receiver position using the theta and phi angles. If it is monostatic RCS, you simply go with the second option, calculate fields in plane wave incident direction. Okay, that will make it monostatic RCS. Okay. So if I click on create, then we request it for RCS. So you need to just save the model and run it. So instead of trying to run it and waiting for an answer, what I will do is I will open RCS of a sphere, which is pre-computed. So you can see here, this is RCS of the sphere over a frequency range. So most of the times we try to use these kind of examples because most of you might know already sphere being a standard shape, which you can easily define using an equation. You can even calculate the RCS by hand calculations and compare your simulation results. So this is expected RCS from a sphere. Now that we looked into the workflow of setting up RCS simulations in Feko, now let's look into different solvers that are available in Feko for calculating RCS of different targets. If you remember that one introductory slide for Feko, there are multiple solvers available in Feko, right? Of all those solvers, these are the solvers that I would recommend for calculating RCS. Okay. First is method of moments, which is the default solver in Feko. Whenever you are using Feko, if you don't specify any solver, Feko will always use method of moments. So that's a default solver. Okay. And it's a fully featured implementation in Feko, being so it can handle any types of geometries. Okay, so you can have targets which are 3D arbitrarily shaped, which are made up of many different materials, whether they can be metals or dielectrics, combinations of metals and dielectrics, or they can be composites as well. Yeah. So there are no limitations on what type of materials you can have for your targets. Okay. But method of moments is good if the target size is electrically small. Okay, so it's computationally very efficient. It's fully parallelized. If you have a machine with multiple cores, so you can take advantage of all the cores. Okay, but if the target is electrically large, then the memory and time requirement for method of moments will increase exponentially with the size. For example, if you double the frequency, typically the number of unknowns are increased by 4 times. Okay? When the number of unknowns are increased by 4 times, the memory and time requirements for method of moments will increase by 16 and 64 times, because the computational resource requirements for method of MEMS are in the order of n square and n cube, where n are the number of unknowns. Okay? That's why when n is increased by 4, memory will increase by n square, which is 4 square 16, and time will increase by n cube, 4 cube, which is 64. Okay? Because of this exponential requirement or increase in the computational resources with method of MEMS, we try to use multi-level fast multiple method whenever the target size is electrically large. Okay? As a rule of thumb, you can use like 5 wavelengths as a rule of thumb. So if the target size is more than 5 wavelengths in size, start using multi-level fast multiple method. Okay? MLFMM is nothing but it is an acceleration of method of MEMS. So accuracy wise, it will be as accurate as method of MEMS. Okay? There won't be any compromise. But in terms of memory and time wise, instead of order of n cube and n square, the memory and time requirements for MLFM will be in the order of n log n and n log square n, which means if the number of unknowns are increased by 4 times, memory and time will be increased by 5 or 6 times with MLFM. Okay? So that's why you can use MLFM efficiently for electrical large structures without consuming a lot of memory or time. Okay? But let's say the size of your target is huge. It's like tens of wavelengths in size or hundreds of wavelengths in size. Okay? And when this target is so huge that you have a machine with a limited amount of memory and you are expecting your answer to be in some reasonable amount of time, you don't have a lot of time to wait for a solution. In both the cases, whether you are either limited by the memory or time, you start looking into the asymptotic methods, physical optics, large element physical optics, or ray launching geometrical optics. Okay? So those 3 are asymptotic methods. When I say asymptotic methods, they involve some approximations. But if you model the problem well within the approximations, you get an answer which is very close to a full wave solution. Method of MEMS and MLFM are full wave solutions, meaning you solve Maxwell's equations exactly without any approximation. That's why you get an accurate numerical solution. Okay? So the main criteria for using asymptotic methods is the target must be electrically large. Okay? You cannot use the asymptotic methods. The approximations won't hold if it is electrically small. Okay? So typically, if the target is more than 10 wavelengths in size, once it is like tens of wavelengths in size, you can start using these asymptotic methods and you can expect reasonable results or reasonable accuracy from those asymptotic methods. Okay? So not only multiple solvers, there are also some additional solver features in Feko. For example, with both method of MEMS and MLFM, you can take advantage of higher order basis functions. Okay? So by default, with method of MEMS and MLFM, Feko will use RWG basis functions, where the requirement would be you need to mesh with respect to the highest frequency with at least like lambda by 10 as your edge length. Okay? But if you have a large target and you are trying to use MLFM, where the target is tens of wavelengths in size, and you are meshing with lambda by 10, you will end up with an enormous mesh. In those cases, you can try to use the higher order basis functions, which does not require as much finer mesh like the default RWG basis functions. So you can use much coarser mesh as long as you're able to capture the shape of the target accurately. Okay. So here, this is an example where you use higher order basis function on a sphere with the order of 3, comparing with the default RWG basis functions with MLFM, and you can see the results are similar between the two. So when you're using higher order basis functions, you are not losing accuracy, but you can definitely save both memory and time. But the most important point is you must be able to capture the shape accurately with a coarser mesh. Okay? If you're not able to capture the shape accurately with a coarser mesh, I won't recommend using higher order basis functions. Okay? If you use higher order basis functions with a fine mesh, you will end up taking more memory and time compared to the default RWG basis functions. So this is another example of an antenna which is solved with the default RWG basis functions, and again solved with the higher order basis functions. So you can see accuracy wise, they both give you the same answer. But when you look at the number of unknowns, you get less number of unknowns because of the coarser mesh. And memory wise, it's like 20 times less memory, and time wise, it is 88 times faster. Okay. So depending on the shape of your target and how accurately you can capture with a coarser mesh, the speed up in terms of time as well as savings in terms of memory will change, but definitely you will see benefit, okay, if you can capture the shape accurately with a coarse mesh. Not only having higher order basis functions, Feko also has something called characteristic basis functions. And this method is particularly useful for calculating monostatic RCS. Okay? So if you are trying to calculate monostatic RCS of a large target, especially targets where you are trying to use MLFM instead of method of MEMS, which you typically use for small targets. Okay? Wherever you are trying to use MLFM and trying to calculate monostatic RCS, the benefits will be much more. You can use CBFM even with method of MEMS. There will be benefits, but the benefits will be much more predominant when you are using it with MLFM. Okay. The way CBFM can save resources, once again, when you activate CBFM, it will reduce the overall number of unknowns by using some macro basis functions. Okay. Whenever the number of unknowns are reduced, automatically you will see reduction in both memory and time. Okay. So this is an example where you are calculating the RCS using MLFM. Once again, comparing with the default RW basis functions and the characteristic basis functions. Okay. So you can see in terms of memory, the savings will be much more predominant compared to time. Okay. Let's say you have a machine with some fixed memory and you're running out of memory, then you can definitely try to fit that problem on the same machine by switching from default MLFM to CBFM. Okay. Instead of 53 gigs of RAM, it took only like 28 gigs of RAM. There is some savings in time, but the savings in memory are much more predominant. And when you are using CBFM, there are two different options. So one is MOM based, the other one is PO based. Okay? And whenever your target is a closed PEC structure, the default solution method in Feko is electric field integral equation. But for closed PEC structures, one can switch to combined field integral equation. Okay? So when you switch to combined field integral equation, then you can use the PO based method where the savings will be much more compared to the MOM based method. If the target is not a closed PEC structure, then you are limited to EFIE, where I would recommend to use the MOM based approach rather than the PO based approach. Okay. So this is an example of an aircraft where you compare both EFIE and CFIE. And you can see, especially for an iterative solver like MLFM, the convergence would be much faster when you use CFIE compared to EFIE. So here instead of 16.5 hours, it took only like 1.5 hour when you are using CFIE. Okay. And this is an example where you are using CFIE MOM based as well as PO based. Once again, if you see memory wise, you will see from the regular default one to switching to MOM based CBFM, there are some savings. When you use a PO based one, there are even more savings in terms of memory. Okay. So time wise, as I said, sometimes there will be reduction in time, sometimes you may not see it, but memory wise, you will see benefit all the time. Okay. So using CFIE and CBFM, that will definitely benefit for closed PEC structures where you can use CFIE and which are also electrically large where you are trying to use MLFM. Okay. So let me show these options in the interface where you can activate them. Okay. So this is an aircraft. So if I zoom in, you can see the enormous mesh on it. Because it has such a dense mesh, so this is electrical large structure. Under the solver tab in Feko, when you go to solver settings, so this is where you have all the different options. The option to activate characteristic basis functions method, as well as the option to activate higher order basis functions. So whether you want to use either HOBF or CBFM, all those options are available under the solver settings. Okay? The first general tab under solver settings, that is where you can activate either the CBFM or the higher order basis functions. Now let's also compare all these different solvers and the accuracy. For an example, like we'll take an example of a ship which is like 120 meters in size, and we'll try to calculate the RCS in the azimuth plane, sweeping from 0 to 180 degrees. Okay? And as we increase the frequency, even though physically it's still 120 meters, electrically the size of the ship will change as we go higher in frequency. So we'll first start with 75 megahertz. At 75 megahertz, the ship is like 30 wavelengths in size. Now, for a ship of 30 wavelengths in size, when we compare method of MEMS, MLFMEM, and higher order basis functions, you can see all the four solution methods, they will give you the same answer. But the difference would be in terms of the memory and time required for each method. Okay. So if you look at the memory, you can see obviously the default method of MEMS, so that will be highest in memory. And when you are switching to higher order basis functions, the memory reduced for method of MEMS. But the size is 30 wavelengths, so it is already electrically large, so we can definitely use MLFMEM. So when you use MLFMEM, the savings were even more predominant, but it took even less memory than method of MEMS higher order basis functions. But when you activate higher order basis functions with MLFMEM, then you can see it took even less memory compared to the default MLFMEM. And when you compare the simulation time, once again, if you see MLFMEM with higher order basis functions, so that stands out to be the winner. So in terms of both memory and time, if you can use higher order basis functions with MLFMEM for an electrical large target, you will have an efficient solution in terms of the memory and time required. Yeah. And with any of these four methods, as I said, you're not losing accuracy, no matter which method you are using. They are all full wave solutions, so they will be as accurate as each other. Now, bumping up the frequency, when you try to calculate the RCS at 200 megahertz, now the electrical size is 80 wavelengths in size. And because it is much larger, now we can use the asymptotic methods like physical optics or ray launching geometrical optics. MLFMEM being a full wave solution, so we can use that as the standard, the accurate solution, and compare the asymptotic solutions of physical optics and RLGO with MLFMEM for accuracy. Okay. Now, if you see at certain incident angles, the asymptotic methods are as accurate as the full wave solution, but at other incident angles, it's not as much accurate. But between LEPO and RLGO, if you see, RLGO is much more closer to the full wave MLFMEM solution. Okay. The reason being, by default, physical optics does not take multiple reflections into account, whereas ray launching geometrical optics will take multiple reflections into account by default. Okay. So that is why if you compare just MLFMEM with RLGO, you can see how close they are. So an asymptotic solution like RLGO can be as accurate as a full wave solution like MLFMEM, provided you are using it for an electrically large structure. Okay. Another benefit of using RLGO is with physical optics, you will be limited to metallic structures. Okay. But if the target involves some dielectrics, let's say you are trying to add some radar absorbing materials on your target to minimize RCS. Okay. Whenever there are some dielectrics involved or combinations of metals and dielectrics, then I won't recommend using physical optics because of its limitations in handling dielectrics. That is where you need RLGO. RLGO can be used with metals, with dielectrics, combinations of metals and dielectrics, and it will also take into account the multiple reflections by default. That's why you can see the accuracy of RLGO is very close to a full wave solution like MLFMM. But in terms of memory and time, any asymptotic method will take a lot less memory and time compared to any of the full wave solution. Okay. With MLFMM, here we are looking at more than 100 gigs of RAM, but with RLGO, it took in megabytes, not even gigabytes. Because RLGO can handle dielectrics, we have an example where you're trying to solve for RCS of a ship and taking into account the effect of C, okay, the rough surface. Okay. We have a script that we use to generate this random rough sea surface, and we have ship on top of that sea surface and try to calculate the RCS and see the effect of the sea surface on the RCS. Okay. And here you can see the difference between these two computations. So one is with the rough sea, one is with the smooth sea. Okay. Obviously, there are some differences, but not predominant in all incident angles. In certain incident angles, it's more predominant compared to the other incident angles. Okay. But by requirement, if you want to take into account all the different effects of the roughness of the sea, you can. That's possible to do it in Feko. And when it comes to visualization of the results, obviously from all the previous results, you can see you can always plot RCS on 2D graphs, but it is also possible to visualize RCS in 3D. Okay? To visualize RCS in 3D, all you need to do is request for RCS in all the different incident angles, okay, instead of one specific incident angle or just sweeping in one cut plane. Okay, so if in Feko, when you request for RCS in all possible incident angles, then when you plot RCS in post Feko, you'll be able to look at the RCS in 3D, okay, like the image that you see. So if I go back, let's say here for this target, now instead of a single cut plane like this, what I would recommend is you need to request for RCS over the entire sphere, and you can specify all the different incident angles. Okay, so you can see theta sweeping from 0 to 180, phi sweeping from 0 to 360, and because both theta and phi are varying, you need to specify an increment. Okay, now when you request for RCS for all these possible incident angles, when you plot the 3D results in Feko, you'll be able to look at the 3D RCS. So not only looking at the 3D RCS, but let's say you're trying to calculate the ISR images. Okay? That is also possible in Feko using scripting. Why I'm referring to scripting is for both pre-processing and post-processing, we have a fully implemented API using Lua scripting. Okay? Anything that you want to automate in terms of pre-processing or in terms of post-processing, it's always possible to automate it using Lua scripting in Feko. Okay? And for ISR imaging, we already have a macro that is already built, so you don't need to spend time for writing the script from scratch. We can always share that script. In fact, the script along with an example model is available on the Altair community page. So this is the link to it. So you can download the script and you can use it if you want to plot the ISR images for any of your RCS targets. So that's on the post-processing, not only just 2D RCS graphs, so you can do 3D, you can plot ISR images, but when it comes to materials, not only handling homogeneous materials, Feko can also handle composites. Okay? So this is an example. We have a fighter plane here. So instead of just a metallic structure, if you want to have composite, either to reduce weight or to for any other reason, let's say instead of using looks like my slide automatically restarted. So let me share the slides again. Looks like some update installed automatically. Sorry about that. Now coming back to the composites. Yep. So if you are trying to handle composites in Feko, Feko allows you to define the composite materials. You can first define all the different fiber materials, the different epoxy, and then you can define the layered anisotropic material and specify the fiber orientation and assign that material to the geometry. And when you try to solve, Feko will take into account the effect of the fiber alignment and the material properties. Okay. This is an example here where you have carbon fiber with the different alignments along the fuselage as well as on the wings. And because of the fiber alignment, the way this structure interacts with an incident field will change. If it is just metallic, then it interacts in a different way compared to if it is carbon fiber. You can look at the surface currents that would make it much more clear. So if you have an incident field like this on the body of this aircraft, and depending on the fiber orientation, if it is metallic, you will have this type of current distribution. But because if it is carbon fiber, and if the fiber is not in, or if the E field vector of the incident field is not aligning with the fiber direction, then the incident field actually cannot see that structure. Okay? And there won't be any incident field on it. So here, when you have a plane wave incident vertically, the E field vector is along the direction of the wings. That's why you see the surface currents just like the metal, but on the body, the fuselage, because the E field vector is orthogonal to the direction of the fiber, the fuselage is not visible to the incident field. That's why you don't see any induced currents. Okay. Now, conversely, so you see the other one. So for all these different incident angles, if you compare the RCS of a metallic body to the carbon fiber, you can see the difference. So here, in one case, the carbon fiber has a lower RCS compared to the metal. In the other case, the carbon fiber has a higher RCS compared to the metal. Okay. So depending on the orientation of the fiber and how it interacts with the incident field, the RCS will definitely change. Well, let me show that again. Using an example. So here, as I said, you can define the materials for all the different fiber, the epoxy, and then define layered anisotropic materials. Okay? So if you go and if you look into the media, these are all the different types of materials that you can define: dielectrics, metals, layered dielectrics. So this is homogeneous. The other one is anisotropic layered. Okay? So if you select anisotropic layered, it will ask you for the material in the principal direction as well as the material in the orthogonal direction and the reference direction and the thickness of each layer. Okay, so you can define a composite with multiple layers as well. So here I have two different composites where the alignment is 0 as well as the alignment is 90. And these two materials, they are assigned on different parts of the aircraft. Okay. So it's possible to have many different types of materials, many different types of composites also within the same model in Feko. So that's on how to calculate RCS in Feko, what are the different solvers available in Feko for computing RCS, the different solver options like higher order basis functions or characteristic basis functions, and the different types of materials that Feko can handle. Okay. Hope that gave you a clear overview of Feko capabilities for computing RCS. It's a very powerful tool with many different solvers and solver features. So it should be definitely useful to calculate RCS of any given target. Okay. But before closing out, let's also look into some of the useful resources Altair is providing for students. The most important one will be the free software, obviously. Please note that fully featured Feko software is available to all the students for free. All you need to do is you need to register for an Altair One account using your student email ID, and then you will be able to request for a full license without any charge. So I would recommend all the students to take advantage of it. Along with the free software, there are also several e-learning modules. There are some live trainings. You can always register for a live training which is virtual and you can attend and learn Feko. But let's say you are trying to learn at your own pace, then you can take advantage of these embedded courses which are like pre-recorded trainings. There are recorded training courses on different topics, getting started, applications, solutions. Okay, feel free to go through these training courses to learn Feko and use it productively for any of your project. And if you need help, whenever you're trying to use the software, if you need help with anything, please take advantage of Altair community. It's a great place, not only to seek help, but also to interact with other Feko users. Okay. You can always have discussions on different topics, but if you need help with anything, you can also post a question. Other users can respond, but the Altair employees who are in the high frequency electromagnetics team, they also monitor this community. So they will also chip in and try to answer the questions if no user is answering your question. Last but not least, I would recommend this book as well by Dr. Reddy, who is the Vice President of Business Development with Altair. But you all might have known Dr. Reddy through his long association with IEEE. He is the current president-elect, so he'll be serving as the president of ABS next year. So this is a great book to learn antenna design analysis, but using some examples that are solved using Feko. So thank you all for joining today. I hope you got a chance to learn about the capabilities of Feko for RCS analysis, along with some basics of RCS, where it is useful, how it affects our daily lives. Okay.